And then, let's start the afternoon session. So the first talk will be about applicative bidirectional programming with lenses by Kazutaka Matsuda from Tohoku University. So let's give it away.
Okay. Hello, I'm Kazutaka Matsuda from Tohoku University. So it's joint work with Monwan from the University of Kent. So today I will explain our new bidirectional programming framework in which we can write bidirectional programming in applicative style with higher functions. So we can write bidirectional programming as usual programming. So first of all, I will explain the background of this research. That is, bidirectional transformation. So bidirectional transformation is a pair of functions called get and put. I use an example to explain the bidirectional transformation. So assume that we have a table that containing laboratory members, so with names and account names and room numbers. And assume that we are only interested in the names and account names and transform this data to that data. So get is just an ordinary function like this transformation. So in such a situation, it is sometimes convenient if I can update this source data by updating the view data. So assume that we change my account name from KZTK to KAZ as this. So we use put to reflect this update. Concretely, put takes original source data and updated view data to produce the updated source data. So bidirectional transformation is this pair of get and put. So there are many applications of bidirectional transformations, but I do not explain this in detail. Anyway, bidirectional transformations are just two functions. So we want to require some properties to bidirectional transformation to characterize reasonable bidirectional transformations. So here we consider property called well-behavedness. So well-behavedness consists of two properties. So one is acceptability, the other is consistency. Very roughly speaking, acceptability means that if there is no update on the view side, there is no update on the source side. And consistency says that put correctly reflect the view update. So, and if you update a view and put this update back to the source, and if we get that again, so we obtain the same view. So, however, if we write bidirectional transformations or the pair of functions manually, so it is quite likely that we obtain non-well-behaved bidirectional transformations. So even though we obtain a bidirectional transformation at some well-behaved bidirectional transformation at some point, so if we change one of the programs in some reason, we have to change the other accordingly to the change. So to avoid such a problem, so what we want is bidirectional programming language or bidirectional programming framework to write well-behaved bidirectional transformations. So one of the existing framework for bidirectional transformation to write bidirectional transformation is lens framework. So lens is also a name for a building blocks using the lens framework, so which is an encapsulated pair of get and put. In the lens framework, so we write bidirectional transformations by composing lenses by using lens combinators. So here is an example of lens programming. So as you see, so we compose lens parcel by using lens combinators black dot to construct a bigger bidirectional transformation or lens. So I do not explain the detail of such kind of lens and lens combinators. What is important here is that we compose lenses by using lens combinators to construct bidirectional transformations. And in the lens framework, such kind of lens combinators are well-behavedness preserving. So since we compose well-behaved lenses by using well-behavedness preserving combinators, so we can guarantee that the constructed bidirectional transformations are also well-behaved. This is the key point of the lens framework. However, there is a problem in the programming in lens. So in lens programming, so we have to program bidirectional transformation with somewhat unfamiliar combinators in a point-free style. So this is quite okay for reasoning, and this is also key to guarantee the well-behavedness in the lens framework. However, this is not so much good to write or read involved programs. So our goal is to overcome this problem. So our approach to overcome this problem is to represent lenses as functions. So specifically, we provide lift-end function that takes NRE lenses to produce NRE functions. So since now lenses are represented as functions, so we can freely use lambda abstractions and function applications, so which leads to flexibility of a programming style. So also the functional representation of lenses has a main advantage to access. We have more access to the host language in an EDSL style implementation, especially so we can compose bidirectional transformation by using ordinary higher functions. So then I will explain the intuition about this LT type. So very roughly speaking, this LT type represent bidirectional expressions. So in a sense, the lifted function takes a bidirectional expressions to construct bidirectional expression. So this construction itself is not bidirectional. And only bidirectional things in our framework is LT type. So, but lifted function constructs a bidirectional expression from bidirectional expression, preserving some property. So this is the key to guarantee well-behavedness in our framework. So this is a contribution of our work. So we made bidirectional programming framework in which lenses are represented as functions. So even though we have such kind of flexibility of programming, so bidirectional programs constructed in our framework are guaranteed to be well behaved. And our framework simplifies bidirectional programming in the sense that bidirectional programming in our framework is quite similar to the programming just get. So from the next slide, I will explain the bidirectional programming in our framework. So first of all, I will explain the core APIs of our framework. So as I have explained, so we provide lift function that takes NRE lenses to produce NRE functions. So our framework also provides unlifted function, so which is the left inverse of lift function. As I explained before, these LT types represent bidirectional expressions. And what is important here is that this LT type is treated as abstract type in our framework. So since the LT types are abstract, so only the way to manipulate LT types values are by using lifted functions. So this is key. This is key in our framework to guarantee the well-behavedness. Anyway, I will explain the programming example in our framework. So I will explain the simplest example first, that extracts the first component of pairs. So this is our bidirectional version of a first. As you can see, its implementation is identical to the unidirectional first. So only the difference is that we write transformations on LT type values. So, yeah, actually, this is how we program bidirectional transformations. So we write transformations on LT type values to implement bidirectional transformations. From the transformation on LT type values, we can obtain length by using unlift function. So, for example, as this, so we apply the unlift to function to first f, we obtain the length first L. So, this is the behavior of a first obtained length. So, if we apply get first L to the pair of 1 and 2, we obtain 1. So, and if we update this 1 to 3, so, and reflect this view update to the original source, we obtain the pair of 3 and 2. So, let us explain the much more involved example, unlines. So, which is a simplified version of the example that I explained in the beginning of this talk. So, unlines function takes a list of strings and returns the strings obtained by concatenating the strings with new lines, like this. If we use unidirectional language such as Haskell to implement unlines function, so it can be written as this. So this is nothing surprising. So unlines is a function, takes a list of strings and returns a string. And for the new case, it returns empty string. And for the const case, it concatenates two strings with a new line. So let us explain how to program bidirectional version of unlines. So this is bidirectional version of unlines in our framework. As you can see, our bidirectional version, unlines F, has a quite similar structure to the unlines, unidirectional unlines function. So there are two main differences between the unidirectional version and our bidirectional version. One of the differences is that, as I explained before, unlines F function is a transformation of LT typed values. Another important difference is that to produce or to transform LT typed values, we use lifted lenses. So here we use the new function to lift constant lenses, and here we use lift to function to lift the binary length. So from the definition of unlines F function, so we can obtain the length unlines F by using unlift function. So here unlift T function is a variant of unlift N function, but I do not explain the detail in this talk. So anyway, I explain the behavior of the obtained bidirectional transformation. So if we apply get unlines F to the list of these strings, so we obtain this string. Actually, forward behavior is the same as the unidirectional version of unlines. So, and if we change these strings to that string, and if we reflect this update back to the original source here, we obtain this list of strings. I believe this behavior is intuitive one. So, however, there is one thing to explain. So there is a limitation of our framework. So we cannot change the number of new lines in the view. So to reflect such kind of update, we have to change the length of the source list. However, look at this type. So unlift F is a function from list of LT types to LT type. So what is important here is that list occurs outside of LT type. So, and recall that AT types are only bidirectional thing in our framework. So this list and list manipulation itself are not bidirectional in our framework. So we cannot change the length of list. So this is the limitation of our framework. So there is a trade-off between programmability and updatability. So, and look at this function. So one might notice that this unlines f function can be implemented by using for-dial function. Yes, we can do it in our framework. So as you can see, we can compose bidirectional transformations by using ordinary higher functions in our framework. So let us explain the main theorem. So for any function of this type in which lifting functions are applied only to well-behaved lenses, and if we unlift these functions, the obtained lenses are guaranteed to be well-behaved. So I do not explain the proof of this theorem, but I want to mention that this theorem can be proved by using free theorem. The key is that LT type is abstract in our framework. So only way to manipulate LT type values are lifted function. So there are some topics included in our paper, but not in this talk. So if you are interested in these, some of these topics, please read our paper. So now let us discuss related work. The most related work to our framework is semantic bidirectionalization, which derives well-behaved bidirectional transformations from only from polymorphic get function. More concretely, it provides BFF function that takes polymorphic get functions and returns corresponding put function. Our framework subsumes semantic bidirectionalization because we can implement BFF function by using lifting and unlifting functions. So another important related work is van Lahoven representation of lenses, which is used lens package in Haskell. In this representation, length from A to B is represented as function type of this. So intuitively, this is a function that takes effectful update on the view and returns effectful update on the source. So, however, there is no guarantee of well-behavedness in the framework. So if we use these functions as functions, so in the sense that the free use of lambda abstractions and function application. Also, I want to mention that bidirectional programs in the framework sometimes get different from programming of get, especially when we use higher functions. So let us conclude this talk. So we made bidirectional transformation in which lenses are represented as functions. Even though we have such kind of flexibility, so bidirectional transformations constructed in our framework are guaranteed to be well-behaved. And in our framework, as we have shown by using examples, bidirectional programming is quite similar to programming JavaScript. So this prototype implementation can be available from this URL. Thank you.
So does this framework generalize to polymorphic lenses when you can update something and change its type?
Maybe this is difficult, I think. So, but I do not remember the reason. So I consider this problem and I find it difficult, but I do not remember the reason here.
Can you go back to the slide with the problem about changing the length of the list?
Sorry?
Can you go back to the slide with the problem about changing the length of the list? You had the type of unlines. Yeah, so it's a list of LT strings. That's fine. And because it's only LT that's bidirectional, not the list, you can't change the shape of the list. If you had, could you write the function of type LTS list of string to LTS string, and would that allow you to change the shape of the list as well?
Yes. So this, yeah. In the paper, we include such kind of discussion. So to do so, we lift length combinator also.
What is this S that keeps popping up? And these for all S's, you haven't really mentioned them. I've seen them before, but they're, so what role are they playing here? Can you give us any intuition?
This you are talking about. This S.
That S, it sort of pops up all over the place in the tights, but it didn't appear in your soundtrack.
Yeah.
I'm sure it plays an important role, so I was wondering if you could tell us why it's there.
Yeah. So I have theoretical explanation reason or some implementation reason to include this S type, but I do not have any intuition under why we need this S and what is this S. Yes. So.
Is there time for a quick one? So if I define view x as x paired with x, and then turn that into a lens, then the put function isn't well defined, is it, for pairs with different components? What happens in your library if I do that?
Sorry, so I cannot hear you. So
if I define view x returns x paired with x, so I duplicate the input, and then I lift that to a lens, then the put function isn't well defined, is it, on pairs whose components are different? So what happens?
So we only allow the updates that changed the 2x simultaneously to the same value.
So what happens if I apply the put function to a pair with different components?
So it fails.
Okay.